When the bleep are we going to use that?
The Skytower ride in Denmark is one of the world's scariest theme park rides. The ride's located at Denmark's Tivoli Friheden theme park. Friheden translates to freedom, which is appropriate since the Skytower is a controlled free fall. It's the only ride in the world that safely, lets park guests drop 100 feet or 30.48 meters for Denmark and the rest of the world. Oh my God! The ride lasts about 2.5 seconds from the moment you are released to the moment you hit the net. The net safely slows you down to a stop in 1 second. Let's analyze how the forces, velocities, and accelerations all interact to create this wonderful ride. When the ride begins, the passenger hangs from the top of the tower. Then they accelerate towards the ground, speeding up, and they slow down once they hit the net. At all times, gravity's pulling down on the object. In this case, there has to be a force holding it in place. Gravity's pulling up, a tether is creating a tension force holding them in place until the operator pulls the pin. If you know the passenger's mass, you can use Fg equals 9.8 times mass to find their gravitational force. 70 times 9.8 gives us 686 newtons. Now, I know these are balanced forces, so Fg equals Ft. The gravitational force equals the tension force. So if I'm pulling down with 686 newtons, I'm pulling up with 686 newtons as well. We can use the kinematic equations to find other information. We know that we start at 0 meters per second. We're stopped at the top of the tower with balanced forces. We travel 30.48 meters in 2.5 seconds. If I wanted to find how fast I was moving at the end of this first motion, so right before I hit the net, I'd be looking for my final velocity. My acceleration's not included. If I know what's not included, I can find the formula that does not include acceleration. My given information can all be substituted in now. X is 30.48, 0 is initial velocity, and t is 2.5. I'm going to simplify a little. 2.5 times 1/2, divide both sides by 1.25, and since v plus 0 is just v, there's my answer. This represents how fast I'm moving. So I need to make sure that my answer is both reasonable, which means I want a higher velocity than 0, and it has the proper unit, meters per second, which is the unit for velocity. Let's analyze that same motion, the drop. If we know we started at 0 meters per second, we're traveling or falling 30.48 meters downward. In 2.5 seconds, I want to find the acceleration. So let's say that v is not included. My final velocity is not included. I'm going to find a formula that does not have final velocity. I have acceleration, time, position, or distance, and initial velocity, but not final. Again, substitute in the information you know, and then it's just a little algebra. 0 times 2.5 becomes 0, so it's gone. I'm going to simplify. 2.5 squared is 6.25. 1/2 of that is 3.125. If I divide both sides by 3.125, I get 9.7536 as my acceleration. If you notice, this is close to 9.8 meters per second squared, which is the acceleration of objects without air resistance. So to explain why we're observing a smaller acceleration, we need to look at the forces that are present. Let's look at the forces that are taking place in between the top of the tower and the net. The passenger's accelerating, speeding up before they slow down when they hit the net. So gravity, no matter what, is pulling down. Something is pulling up because we're not getting the normal 9.8. Gravity's pulling down. We can chalk up that unbalanced force to friction, air resistance. We can call this drag. If I know the mass of the object, I can find its gravitational force, just like we did before. It's still 686 newtons. But now I need to find what my friction force is. How much force is causing this drag? I need to use Newton's second law. Net force equals mass times acceleration. I know the mass, and I found the acceleration, 9.75. I'm going to multiply those together. 682.5 is the net force. It's the difference between the up force and the down force. In this case, because we know we're accelerating downward, we're speeding up downward, we are going to have a smaller force upward, a bigger force downward. So I'm going to take 686 minus 682.5, and that tells me 3.5 newtons. There is 3.5 newtons of drag caused by air resistance. That's what causes the smaller acceleration. Right before the passenger hits the net, they're moving 24.38 meters per second, and the net slows them down to 0 meters per second for a brief moment. This happens over the course of about 1 second. I want to find the acceleration. How much or at what rate is this net slowing down the passenger? So we're looking for acceleration. X is not going to be included. So we need to find a formula that does not have x, or displacement, distance, included in it. I'm going to plug in what I know. 0 is my final velocity. A is still A. 1 is my time. I'm going to subtract 24.38 from both sides. A times 1 is just A, so that's my acceleration. Negative 24.38 meters per second squared, which is pretty reasonable. We went from 24.38 to 0 in 1 second. Let's finish by looking at the forces acting on the passenger at the very end of the ride, when they hit the net. They accelerate, speeding up, and then slow down because the net is now pushing up on them. No matter what, gravity is still pulling down on the passenger the same exact amount. However, to cause an acceleration to go from 24.38 meters per second to 0, it's going to require a big outside unbalanced force. In this case, because our acceleration is pointing upward, all of our highest velocities are behind the passenger, our highest force is going to be pointing up. Gravity's pulling down the normal force caused by the net's pushing up. Mass is still 70 kilograms, so we can find the gravitational force. However, since we have unbalanced forces, we need to find the net force, how much bigger that upward force is. I'm going to multiply mass times acceleration. In this case, because we're finding the net force, it's okay to leave the negative out because we know we're going to add it onto the top force. Net force is 1,706.6. That means the net needs to push up 1,706.6 newtons more than gravity's pulling down. That's why we have to add gravity's force plus the net force. That means the normal force has to apply 2,392.6 newtons in an upward direction, or the person who fell off the tower is going to go straight through and sue the theme park. In summary, the Skytower passenger starts with balanced forces. Because they're held in place by a tension force that is equal to their gravitational force, they then start to accelerate, speeding up at 9.75 meters per second squared, reaching a velocity of 24.38 meters per second downward. This is due to unbalanced forces caused between gravity and the drag caused by air resistance. Once the passenger hits the net below, they slow down, accelerating to a velocity of 0 meters per second due to the outside unbalanced force caused by the normal force of the net. Despite the fall, an acceleration of 24.38 meters per second squared spread out over a second is still safe for humans, who can handle accelerations of up to 49 meters per second squared before passing out and ultimately suing the theme park.